What happens when the deep bones of an island arc begin to grind, twist and slip in near unison? Could a violent pulse beneath Mindanao send a silent ripple northward through the archipelago's fractured crust, stirring dormant faults along the Visayan seafloor? In the early morning hours of October 10th, 2025, that question may have found its first uneasy whisper. A powerful magnitude 7.4 earthquake struck off the eastern coast of Mindanao near Santiago, Davao Oriental. Its epicenter located roughly 20 kilometers, 12 miles, east of the shoreline and about 25 kilometers, 16 miles, beneath the surface, some 65,000 feet into the descending Philippine Sea Plate. Within minutes, seismographs across the country lit up as the tremor propagated through the mantle, wedge and crust, shaking the entire southeastern region of the Philippines. This was not an ordinary thrust quake. Data from PHIVOLCS and the United States Geological Survey showed an oblique reverse fault mechanism, meaning the rupture involved both vertical compression and horizontal shearing. The Philippine Sea Plate subducts west-northwest beneath the Sunda Plate at an average velocity of about 100 millimeters per year, roughly 4 inches annually. That constant motion compresses and bends the overriding plate until accumulated stress suddenly releases along the interface, producing a rupture tens of kilometers long. Modelling of the October 10th event suggests the fault plane measured approximately 75 by 30 kilometres, 47 by 19 miles, releasing energy equivalent to nearly 200 atomic bombs. Slip inversion solutions indicate that portions of the fault move by as much as 4.7 metres, 15 feet, during the event, massive displacement even by trench standards. Unlike continental quakes that fracture the ground surface, this rupture occurred entirely offshore and at subcrustal depth, leaving no visible scar on land. That absence of surface rupture is typical for subduction interface earthquakes. The strain is consumed within the ductile layers of rock beneath the ocean floor. Yet, despite its submarine origin, the quake was powerfully felt throughout Mindanao. Ground acceleration readings exceeded 1G in certain stations along Davao Oriental, reflecting intense shaking produced by the sudden release of elastic strain along the Philippine Trench. The nature of the faulting was particularly revealing. Focal mechanism beach ball diagrams indicated either a moderately dipping south-southeast striking reverse fault with left lateral motion or a northeast striking reverse fault with right lateral motion. Both interpretations imply oblique convergence, an interaction consistent with the arcuate geometry of the Philippine Trench, where compression and shear combine in complex fashion. In essence, the crust here is neither purely colliding nor sliding. It is doing both simultaneously. Such mixed-mode faulting is geologically efficient in releasing stored strain, but it also redistributes stress into neighbouring fault systems, setting the stage for aftershocks or distant secondary events. Indeed, in the hours that followed, PHIVOLCS logged hundreds of aftershocks, many between magnitude 4 and 6. These clustered mainly along the trench axis northeast of the Mainshock, gradually migrating both down dip and along strike, a pattern typical of stress diffusion along a subduction interface. As the crust around the rupture adjusted, some aftershocks occurred within the subducting slab itself, signifying internal bending of the descending plate. By the second day, more than 45 aftershocks had already been recorded, with magnitudes reaching 6, and thousands more would follow in the ensuing week. But the seismic story did not end there. Roughly 10 hours after the initial shock, a second major rupture, measuring magnitude 6.7, struck only a few tens of kilometers away at a depth near 60 kilometers, 37 miles. This doublet event echoed the same oblique reverse mechanism as the first, but likely slipped on an adjacent patch of the plate boundary or a splay fault within the downgoing slab. Doublet quakes of this kind reveal that the first rupture did not release all accumulated strain. Instead, residual stress transferred laterally, loading a neighbouring fault segment that failed soon after. Together, the 7.4 and 6.7 events released centuries of stored elastic energy along the trench front, reconfiguring stress fields across the southern Philippine arc. When a major rupture breaks, it alters the surrounding Coulomb stress, the combined effect of shear and normal stress acting on potential fault planes. Some nearby regions experience an increase, promoting further failure. Others experience a decrease, inhibiting slip. The Mindanao doublet's cascading pattern implies immediate stress loading on contiguous fault sections, leading to rapid successive failure. This mechanical domino effect explains both the tight timing and the expansive aftershock field extending north-northwest along the trench. Seismic tomography from earlier Philippine trench studies suggests the presence of hydrated minerals and high-pressure fluids within the subduction interface. These components can lower friction, allowing slip to propagate more easily and influencing how stress transfers along the plate boundary. When fluids are expelled during rupture, they can migrate laterally, triggering slip on nearby fault patches. Thus, fluid-driven stress redistribution may have contributed to the Mindanao doublet's complex propagation. Historically, subduction doublets are rare but not unprecedented in the Philippines. The March 2002 Cotabato earthquake, for example, displayed a similar pattern of a main thrust rupture, followed by a strong oblique aftershock. The December 2023 Davao event also featured secondary ruptures along the downgoing slab. Yet the 2025 sequence's brief separation of roughly 10 hours between large shocks is unusually short, implying tight mechanical coupling across fault patches. Geodetic networks have already captured centimetre-scale crustal displacements consistent with post-seismic afterslip. INSAR satellite images reveal subtle ground deformation across eastern Mindanao, confirming that the rupture propagated offshore with no surface break but left measurable strain on land. GPS stations show horizontal shifts of several millimetres across the island, evidence of elastic rebound following the quake. From a tectonic standpoint, this doublet reflects how the Philippine Trench accommodates oblique plate convergence through both thrust and strike-slip motion, a textbook example of strain partitioning. The vertical component is taken up by subduction along the trench, while horizontal motion is absorbed inland by the Philippine fault system, which bisects the archipelago from Luzon to Mindanao. When the trench releases energy, stress can migrate laterally into the fault system, sometimes activating segments hundreds of kilometers away. This migration of strain sets the backdrop for seismic unrest farther north. By late September, seismographs near northern Cebu had already recorded a growing swarm of small tremors. Then, on September 30th, 2025, a magnitude 6.9 earthquake struck roughly 10 kilometers, 8 miles, east of Bateria in northern Cebu. The rupture occurred at a shallow depth of about 10 kilometers, 33,000 feet, along what Fivolks later identified as a previously unmapped right lateral strike-slip structure, now called the Bogo Bay Fault. The Mainshock ruptured approximately 1.5 kilometers, about a mile, of this submerged strand, displacing it laterally by several tens of centimeters. Over the next 10 days, more than 10,000 aftershocks were detected, the largest being magnitude 5.7 in the early hours of October 13th near Tambongon, only 2 kilometers, about 1 mile, south-southeast of the city. That 5.7 aftershock, though far weaker than the Mindanao Trench doublet, was the most intense in central Visayas in years. Its shallow depth allowed seismic waves to reach the surface with remarkable intensity, producing ground shaking measured at level 7 on the Fivolks earthquake intensity scale. Technically, it was an aftershock of the September 30th Cebu Mainshock, not the Mindanao event, yet its timing, arriving just 3 days after the Davao rupture, renewed debate about whether a slow redistribution of regional stress might be propagating northward through the Philippine arc. Seismologists describe the Bogo Bay Fault as dextral, meaning the opposite sides move rightward relative to each other. This motion accommodates lateral shear within the Visayan block, caught between opposing forces of the Philippine Trench to the east and the Negros Trench to the west. The Visayas function as a tectonic hinge between two subduction systems. As these trenches continue to pull the crust in opposite directions, internal strike-slip faults develop to relieve torsional strain. The October 12th to 13th events thus represent local readjustments within this pivot zone. What makes the Cebu sequence geologically compelling is its apparent autonomy. Prior to 2025, the Bogo Bay Fault had no mapped surface trace and was considered inactive. Its sudden reactivation underscores how incompletely the nation's offshore fault networks are understood. Seismic reflection data long hinted at buried fractures beneath the Visayan Sea, but their behavior remained uncertain. The new earthquakes now confirm that these structures can indeed slip seismically, possibly linking to deeper lithospheric faults that accommodate rotation of the Visayan block itself. The sequence also raises a persistent mechanical question. How does strike-slip motion on a small crustal fault relate to the broader stress regime of a subduction system hundreds of kilometers away? Some numerical models propose that after a major trench earthquake, elastic relaxation within the subducting slab can transmit minor stress perturbations laterally, subtly altering stress fields in adjacent regions. If a nearby fault is already critically stressed, even a minute increase on the order of a few kilopascals can trigger failure. Whether that mechanism operated here remains speculative, yet it fits the pattern of near-synchronous activity across multiple Philippine segments. If the recent Mindanao doublet and the subsequent Cebu rupture seem like isolated tremors, history argues otherwise. The Philippine archipelago has always operated in cycles of clustered seismicity, episodes lasting several years, during which strain shifts progressively from one fault system to another. The October 2025 sequence, therefore, cannot be viewed in isolation. It belongs to a lineage of tectonic conversations spanning centuries, each cycle redistributing stress across the same network of trenches and strike-slip faults that carve the nation from north to south. The closest historical analogue remains the 1976 Moro Gulf earthquake, magnitude 8.1, which ruptured the Cotabato Trench and triggered a tsunami reaching 5 to 6 meters, 16 to 20 feet. That event's mechanics, oblique reverse faulting combining vertical compression with lateral slip, mirror those now seen in Mindanao. In the years following 1976, seismographs recorded a slow but distinct migration of activity northward, culminating in a string of magnitude 6 to 7 earthquakes along the eastern Philippine fault by 1978. The resemblance is striking. A major southern rupture followed by gradual activation of faults farther north, a pattern now replaying nearly 50 years later. Another instructive episode unfolded in 1990, when the magnitude 7.8 Luzon earthquake tore through the Dig-Dig segment of the Philippine fault. The rupture extended roughly 120 kilometers, about 75 miles, with left lateral displacement exceeding 6 meters, around 20 feet. Within weeks, smaller quakes flared southward through the Visayas and northward toward the Cordillera. That broad distribution suggested dynamic stress transfer through a lithosphere already under oblique compression, the same structural condition now governing the 2025 cycle. The 2013 Bohol earthquake adds another comparative layer. At magnitude 7.2, it ruptured a previously unrecognized reverse fault beneath the Visayan crust, producing ground uplift of more than 1 meter, 3 feet, and long-lasting post-seismic creep. GPS data tracked deformation continuing until 2017, showing how moderate crustal ruptures can impose regional stress changes persisting for years. Cebu lies only 200 kilometers, about 125 miles, east of that rupture zone, suggesting that residual stress may have contributed to fault reactivation in 2025. Then came the 2019 Cotabato earthquake swarm, a cluster of 3 magnitude 6+ events within a fortnight, each on a distinct strike-slip fault. Fivolk's subsequent analysis described domino style, triggering through static stress increments of merely several bars. That same principle applies today. The M7.4 and M6.7 Mindanao pair released enormous strain, sending pressure ripples northward through the Philippine fault system, effectively priming adjacent faults beneath the Visayan basin. Modern Coulomb stress transfer modelling supports this interpretation. Simulations applied to the 2025 sequence reveal lobes of increased shear stress extending from eastern Mindanao towards central Visayas, overlapping the region where the Cebu event occurred days later. This is nearly identical to post-1976 models, showing heightened stress migrating along the same axis. The conclusion is consistent. The Philippine fault behaves as a continuous mechanical conduit, capable of transmitting stress hundreds of kilometers over timescales of days to years. High-resolution geodetic tools now verify these theoretical models. Interferometric synthetic aperture radar, INSAR, imagery of central Visayas from mid-October 2025 shows opposing deformation patterns, uplift of several centimeters around northern Cebu and subsidence eastward toward Leyte, defining a broad zone of right lateral shear. Such deformation could not arise from a single local rupture. It reflects a complex crustal adjustment involving both the Negros and Philippine trench systems. This leads to a critical question. Are we witnessing the onset of a larger Philippine fault reactivation phase? Although Fivolks has not issued a definitive statement linking these events, the temporal clustering from Davao to Cebu is characteristic of the early stage of a regional stress migration cycle. Similar multi-segment activations have historically preceded major fault system reorganizations. In geological time, these cycles evolve over years, but each event incrementally shifts the mechanical equilibrium of the entire archipelago. Evaluating the potential for a magnitude 8 earthquake in northern Philippines requires merging historical recurrence data with current geodetic trends. Northern Luzon hosts two primary candidates: the offshore Manila Trench and the inland Digdig San Manuel section of the Philippine Fault. Paleoseismic evidence indicates that the Digdig segment ruptures in great earthquakes roughly every 4 to 6 centuries, the most recent being the 1990 event. That rupture released energy equivalent to magnitude 7.8, yet trenching studies reveal adjacent unbroken sections capable of storing additional strain. Meanwhile, the Manila Trench, where the Eurasian plate subducts beneath the Philippine mobile belt, accumulates convergence at approximately 40 to 50 millimeters per year, about 2 inches. Over 3 decades, this motion translates into more than 1 meter, 3 feet, of potential slip deficit, sufficient for a magnitude 8 class rupture under favorable stress conditions. Whether the recent Mindanao-Cebu activity appreciably influences that northern build-up remains uncertain. But stress modelling studies after the 2023 Davao megathrust indicated slight positive stress changes, less than 1 bar, along central and northern fault sections. Though small, such increments can be critical when a fault nears its failure threshold. The Philippine Fault's central links, Leyte, Masbate, and Bicol, thus merit special attention. These segments serve as mechanical bridges connecting the southern and northern blocks. Historical sequences show they often light up midway through regional cycles. The 2020 Masbate magnitude 6.6 rupture was followed by elevated activity in Samar and Leyte, a pattern now repeating with the Cebu quake. In this sense, the current Visayan events may represent another step in a slow-motion progression of stress along the fault spine. Geophysically, this progression exemplifies strain partitioning, the separation of vertical subduction slip and horizontal strike-slip motion across parallel structures. As the Philippine Sea Plate moves obliquely northwest relative to the Sunda Plate, the trenches absorb most of the downward motion, while the inland Philippine Fault accommodates the sideways shear. When one component releases energy, the other tends to compensate, maintaining the regional stress budget. Hence the sequence observed in 2025, subduction zone rupture followed by inland shear, fits established tectonic behavior. Comparable trench-to-fault activation patterns occur worldwide. Japan's Nankai Trough and New Zealand's Alpine Fault exhibit similar chains of stress migration following great earthquakes, often continuing for decades. The Philippines, positioned at a complex triple junction, expresses the same phenomenon more dynamically given the multiplicity of interacting plates. Despite technological progress, forecasting exact timing or magnitude of the next Philippine earthquake remains impossible. Fault frictional parameters, fluid pressures, and crustal heterogeneity render deterministic prediction unfeasible. What can be achieved is real-time hazard assessment through continuous monitoring. Dense GPS arrays, INSAR time series analysis, and improved seismic tomography now allow scientists to detect accelerating strain, accumulation, subtle precursors that might precede large events by months or years. FIVOG's expansion of its digital seismic network, now exceeding 170 stations, enhances detection capability and stress model resolution. Data from the Mindanao-Cebu sequence already contribute to updated probabilistic hazard maps and reveal previously unmapped structures, such as the Bogo Bay Fault beneath northern Cebu. Ultimately, every Philippine earthquake, whether a violent doublet in Mindanao or a moderate tremor beneath Cebu, represents another adjustment within a grand tectonic equilibrium. Each rupture transfers energy, redefines boundaries, and reshapes the surface of the islands. From a geological perspective, the archipelago itself is a transient configuration, continuously re-sculpted by the meeting of oceanic and continental forces. Whether a magnitude 8 event will occur in northern Philippines within our lifetime cannot yet be answered. But the current chain of quakes unmistakably signals that the system is active, the stress is migrating, and the process of adjustment is underway. The Mindanao Trench has moved, the Visayan crust has responded, and the northern faults wait in quiet tension. As of late October 2025, national monitoring remains heightened across the central and northern sectors of the Philippine Fault. No imminent large event has been forecast, but scientists recognize this as a pivotal opportunity to observe stress evolution across an entire convergent margin in real time. The Earth, constant only in its motion, continues to write the next chapter of this geological dialogue between sea and land, trench and fault, compression and release, beneath the expanse of the Philippine sky. If this investigation clarified the ongoing tectonic evolution of the Philippines, support continued factual science reporting by liking, sharing, and subscribing. Tap that hype icon to help this analysis reach wider audiences and sustain awareness of the forces quietly reshaping our islands. Knowledge remains our most steadfast defense against the unpredictable rhythm of the Earth.